Hello, welcome to 24 Hours of PASS, 20 years of PASS, past learnings, and future visions. We're excited you could join us today for Rob Farley's session. Indexes are things that different to 20 years ago. This 24 Hours of PASS consists of 24 consecutive live webinars delivered by expert speakers from the PASS community. The sessions will be recorded and posted online after the event. You will receive an email letting you know when these are available. My humble name is Milan Šarenac. I am a DBA slash full stack engineer, have been for 10 plus years, and so on and so on. I have a few introductory slides before I hand over the reins to Rob. If you require technical assistance, please type your request into the questions pane located on the right side of your screen and someone will assist you. This question pane is also where you may ask any questions throughout the presentation. Feel free to enter your questions at any time, and once we get to the Q&A portion of the session, I'll read your questions aloud to the speaker. You are able to zoom in on the presentation by using the zoom button located on the top of the presentation window. Please note that there will be a short evaluation at the end of the session, which will pop up after the webinar ends in your web browser. Your feedback is really important to us for future events, so please take a moment to complete this. Next slide, please. Okay. Our sponsors, I'd like to take a moment to thank our sponsors, Microsoft and Intel. The staging of 24 Hours of PASS wouldn't be possible without their generous support. I'll try again. Can you hear me now? Okay, let's try again. I'd like to take a moment to thank our sponsors, Microsoft and Intel. The staging of 24 Hours of PASS wouldn't be possible without their generous support, and they are the reason this event is available free of charge. If you would like to learn more about Microsoft or Intel and sign up for information on how they can help you, please visit the sponsors page of the 24 Hours of PASS website. Rob, please, next slide. Thank you. Keep learning all year long with PASS. Visit pass.org and check out all of the free educational resources available to PASS members. Also, don't forget the PASS Summit 2019 will be happening on November 5th in Seattle, Washington. Head over to passsummit.com and register today. Next slide, please. Our presenter, Rob Farley. This 24 Hours of PASS session is presented by Rob.
My headphones have stopped working for a minute. Am I back? Can you hear me now?
Yes, everything is fine. Rob Farley runs LobsterPath Solutions, a specialist data consultancy dealing with Microsoft Data Platform. He's been an MVP since 2006, largely because of his blogging, his presentation around the world, and his dedication to the Adelaide SQL Server user group, which he has led since before the release of SQL Server back in 2005. Rob Farley. Please switch on to the next slide. And that's about it from my side. I will be waiting for any questions, so please feel free to type any, and we will present them to Rob. Rob, please take over.
Excellent. I just had some sort of malfunction with my headphones. I don't know why. I just started hearing only static, but luckily I think it's sorted again now. Hopefully that won't happen during the session. It's always fun when you're dealing with technology. Anyway, let's switch to For those of you who have heard me present before, you'll realize that I don't tend to do slides. And in fact, these days, I don't even tend to do demos. I like to use a kind of a whiteboard approach. I like to explain things in terms of how things work without a computer, because my ultimate goal is to be able to tune queries so quick that you don't even need a computer to be able to do it. You could go to the filing system and get pretty good results that way. So, in fact, I'm doing a whole day in Poland at SQL Day next month, and I'm doing all day without a computer. We're going to have people standing up, holding pages of data, that kind of thing. If they get tired, they can sit down, which will just be an excuse to explain page life expectancy, that kind of thing. Hopefully, it'll be a bit of fun. I figure, you know, worst case, people will learn a bunch of stuff that they remember, even if they end up giving feedback saying, "I wish I could have seen some of these demonstrations." So anyway, this is going to be the area that I'm going to be using today. I'm going to use OneNote with a stylus, and I'm going to scribble on here. So hopefully you can all see that, and hopefully you can see that my writing here says indexes as things that different to how they were 20 years ago. Because of course things have changed massively. Things have improved in all kinds of ways, but a lot of what we still do with indexes is really not that different to how we did them, you know, quite a long time ago. Let me explain a few things about indexes. We'll talk about the things that have changed. We'll talk about the things that that I think you should be seriously considering if you're still doing indexes the way that you did 20 odd years ago. And let's be fair. Let's figure that we're only a few months away from 20 years since SQL 2000 was released. I'm pretty sure SQL 2000 came out at the end of 1999. Despite the name SQL 2000, I'm pretty sure they released it before 2000 actually came around, just from memory. And of course, you may not have jumped into SQL 2000 until a couple of years later. But that's kind of where I want to start our story today. So conceptually, what happened then, and I'm just going to fold my keyboard underneath my surface so that I can write with the stylus more easily. Conceptually, an index is still an index. We start with data, and I'm just going to say let's start with a few pages of data, and we're just going to pretend that they've got information in them that belong to a table, and that these are largely unindexed. In fact, we're going to say this is a heap, which means that somewhere we've got a table which lists, sorry, we've got a page which lists which pages contain the data inside that heap. We might have multiple of these pages, but it's just a list of the pages. And if we want to get data from here without any other index, we just have to look through all of those pages to find the data we want. So this is life without indexes. When we're inserting, we get to insert into a page that has some space in it. When we delete something, we just mark it as deleted and we move on. We would need to rebuild that heap to be able to actually free up space in the file in the database. But on the whole, it's just a heap of data. When we index it, we take a copy of that data and we arrange it in order according to the keys that we use. So if we were to take this data and create a non-cluttered index, we would create a structure where we start filling data up into a page, and we're maintaining that order through the slots that are mentioned at the bottom of the page to be able to say, yep, we're putting this in and it's the first one, so we go slot 0, we put another one in and it's slot 1. Maybe if it comes after the first one, we put another one in. Suppose it goes in between, we rearrange the slots to be able to say, well, actually, this last one that we've got in has to go in at slot 1, and the first one was in there beforehand. It, might be slot 2 now, and so on, so that we can move through the data in order. Once we fill up that page, we then have to do a page split, and at that point we start putting data into, well, whichever page it fits into according to the order. And at this point, we need to have multiple pages containing data, and we need to have a page further up in the structure, which actually helps tell us which page we should be talking about. We have links between them so that we can traverse, or in either direction. But this is what we deal with. Let me actually move that around a bit. This is what we're talking about when we have an index. We have the data in order, okay? An order that we can access. The actual pages might not be in order, they might be all over the place. That's fine. But we can get to this data knowing that if we hit a particular point, all the data on one side of it is earlier and on the other side is later, according to the thing that we've indexed it for. Everything is sortable. If it's a string, we might need to sort it according to the collation settings that are in place. We need to know whether we're sorting them in English or Swedish or Serbian for Milan's sake. And thank you so much for hosting, Milan. It's always great to have a good moderator. I'm sure that as questions come in, you'll happily interject and not fall asleep, given that it must be like 4:30 in the morning or something like that for you now in Serbia.
Thanks for mentioning that, Rob.
Yeah, I apologize. I'll have to try and be incredibly interesting to make sure that you don't drop off. But yeah, we'll see how we go. I suspect that wherever you are in the world watching this, if it's at night time, my dulcet tones will happily soothe you to sleep. I'll try and not be too bad on that. It's a lovely sunny day. It's lunchtime here in Adelaide. I want to say tomorrow. It's Thursday, so maybe you're in New Zealand and it's earlier today. Maybe you're in America and it's still Wednesday. We'll see how we go. So, but the idea being that if we've identified that the particular row that we want is here, for example, we know that all the data on this page, I'll try and draw an arrow that actually looks like an arrow. All the data on this page is before that particular row. All the data that is in a slot on this page, which is earlier, is also earlier than that row. And all the stuff that's after it, or on any subsequent page, is also after it. And this is what gives us the power of the index. The fact that we can find a row by sticking to it, by being able to say, okay, let's figure out which page it's supposed to be in, do binary searches, looking through the data and just going, oh, it must be at this level at the next one, because I can see that maybe I'm looking for the word Milan. Sorry, Milan, I'm going to pick on you a fair bit. We were looking for the word Milan, and we see that one page has everything from L to P, and so we go, great, he must be on that page. Let's go down and explore that. Maybe there's another level and we get to be able to figure out that, and then we get to look through the slots and work out where he is. This is the power of the index, and that hasn't changed, well, since before we had databases. It's how people use filing cabinets. They get to be able to figure out which cabinet they need to go to, which drawer they need to open. They start searching through, and they don't just start at the beginning and work all the way through looking for the one they want. They jump to the middle, and then they jump to the middle of what's left, and so on, and they search effectively for that particular piece of data that they want. They know how things are sorted, and so they have confidence about what's going on. Of course, in a filing cabinet, there's always the worry that somebody has filed it in a different way. You need to understand how that data is sorted. You always hear in comedy shows that people have sorted it according to some other thing, and the person who's trying to get the information out has no idea where to find it. This is the kind of thing that we think about with databases as well, because it's all well and good to say, well, I've got this index which is by the person's first name. If I'm trying to find it by the last name, that index on the first name is not so useful. But still, the concept, it's exactly the same as how it was in the days of filing cabinets. Indexes are still indexes. They provide an order to the index so that you can find the information that you want. They do that according to the order that things are in, and that order is not just for finding, it's knowing that we can actually access things in order. If I'm wanting to count how many people are called Milan, I can then find the first Milan, and then I can look through until the name changes and be able to say, there's 17 of them. I don't know if it's that common a name, but let's go with that. I know that as soon as if I start with the first Milan, and then I'm looking through and I come across somebody who's not called Milan, I know that that's how many I've got. So indexes are not just useful for finding data, they're also useful for aggregating and all kinds of useful things. They're useful for joining and so on, because I know that I can pull the data out in a particular order. So many people miss that with indexes, but this hasn't changed since before we had computers. I say, are they that different to how they were 20 years ago? Well, this is no different to how they were 200 years ago. I'm sure back in the days of, of Roman times, they must have been sorting their data, sorting their scrolls or whatever, however that information was stored. They order things so that they can find them more easily. It's no different to the CD collection that you've still got at home. You either have just a pile of them and you need to look through all of them, or they're in some order so that you can find them effectively. The more data you've got, the better your indexing needs to be, because of the fact that you've got to, you may not be able to fall back to that. I'm just going to look through them all because I know that I'm after the one that is, I don't know what the name is, but it's got this kind of picture on the front, and you start looking through all of them. And that's a scan. That might not necessarily be that great, but the point is, though, that you're starting at the beginning of the index and you're moving through as far as you need to go to be able to find the information that you're after. Now, so the basic concept of indexing, I'm sure you're all across. What would happen in the days of SQL 2000 is you'd run a query and you'd see a select operator appear, and you would see arrows leading to your index seek. If you knew what, if you were able to use a nicely saggable predicate on that, if you're saying where name equals Milan, for example, you would have a seek going on here that's actually telling it, I'm finding the stuff that I want. And in SQL 2000, we would have an operator in here that we don't see anymore. We would often have this thing called a bookmark lookup. Now, I apologize for the fact that you can't read that, but I've just told you it says bookmark lookup, so work with me here, right? That says bookmark lookup. Now, this bookmark lookup would take all the rows that are coming through here, say our 17 Milans, and it would go and do a lookup to find the rest of the information we need, such as what country does he live in, okay? Now, turns out that I know you live in Serbia, but I figure that not all Milans do. Some of them might.
There's only one Milan.
There's only one?
Only one.
Okay.
One
There's only
million.
one. I'm saying there's 17. Let's go with 17. Let's say Milan, if people have had kids and they just go, that guy, Milan, he's a great guy, I'm going to name my kid after him. They wouldn't be thinking about naming their son after a football team or anything like that. No, they're going to name him after the SQL guy in Serbia. So then we find that we've got Milans from all over the world. And we want to be able to find where Milan lives, but we didn't put the country in the index because because back in SQL 2000, the keys that we had could only be 900 bytes. Okay, the keys of the index, the things that we're ordering it by, and actually that hasn't changed. We're still restricted for clustered index keys at least to 900 bytes. I'll come back to this. So what we would do is we would say, well, okay, we've got the first name in there, but if we wanted to store the address and things like that in the index, then, well, we couldn't. We were restricted to 900 bytes. You could declare it on a variable length column, but as soon as you tried to put too much data into that, you'd get an error saying, I'm sorry, it's too big for the keys section of that index. You'd get an error. Even if you had, 1,500 characters allowable in those key columns, it would be okay so long as you didn't try to actually insert more than 900 bytes into it. Bit of a pain, but that's just the way it was, and still is for clustered index keys. It's one of the reasons why we try and keep clustered index keys quite small, because if you try and index them on something that could potentially be quite large, you might actually find that you get errors. Anyway, what this bookmark lookup would have to do is to be able to go back to the underlying table and be able to get the rest of the information. This is we still have this concept. It's just that it's not called a bookmark lookup anymore. These days, we actually don't see that bookmark lookup anymore. We see it says nested loop. And we see that we have another arrow coming into it because the nested loop pulls the 17 rows from that index seek, and then it calls a clustered index key lookup. Or if we have a heap, an RID lookup. As a way of being able to get the information out. It's exactly the same as a bookmark lookup. It's just that it's slightly more obvious about what's going on. Instead of just saying we've got 17 rows pouring into that bookmark lookup operator, it now says we've got a whole separate operator that's being called, and this will say number of executions, again, I'll keep telling you what I'm writing so that you can read it afterwards. Number of executions equals 17. So you have to look up that information that wasn't included in the index. And that was really frustrating because we were limited to 900 bytes. And let's face it, the kind of information that we wanted to pull out of the table was almost never just 900 bytes. And so in SQL 2005, they introduced the concept of included columns. Okay? So 2005, we got included columns. And this meant that despite just having our non-clustered index key of first name and potentially a composite key of first name, comma, last name, if we needed to be able to get something else, but it was too big to be able to have as one of the keys, we could just include it in the index through the included list of columns. And that way we could avoid this whole nested loop section. And then it would look like this. And it would just pass the data straight out of the index into the select, which was really effective. Let me hit undo a few times just so that I can put it back. We'd lose that whole section and an awful lot of work. Because understand here, this seek is one seek operation, right? We can dive into our index and find those 17 rows, and that can be quite effective if we've ordered it nicely. But then each of these lookups is also an index seek. And so this operation is actually doing 18 seeks, whereas if I got my data in my included columns, it's only one seek, because then when it gets down to the leaf level of the index, all the information it needs is right there. So straight away, having included columns meant that in 2005, we could make our queries run way faster. In fact, what would often happen here is that it would say, you know what, to do that, I would need to do 17 extra seeks into the table. Forget it, I'm not going to use this index at all. I'm just going to scan the whole table and look for the information I want. And this is a thing called the tipping point. The point where it becomes quicker just to look through the whole underlying table from start to finish, looking for everything that you want, and lose any benefit of having that index in place versus being able to use the index and find the rows, but then have to do lookups to get the rest of the data, the other columns that you need. We started back in those days in SQL 2000 with the bookmark lookups and no included columns. We tended to find that we only indexed those things that were particularly selective. It wasn't worth indexing anything else because it was just too frustrating to always have it go and, you know, say, oh, there's too many, and go to the underlying clustered index or heap even to be able to look for the data there. In fact, it wasn't just a problem when it was, you know, not selective. It was a problem when stats were out of date, because it might have thought there were only 3 rows in that, but if you've actually got 3,000 rows, it would suddenly need to do all those lookups, and it was a problem. And it's still a problem if you're not leveraging included columns. So if you haven't changed the way you're doing indexes in SQL 2000, there's a point for you right there. Start leveraging included columns to be able to avoid these lookups. Look at your execution plans. Whenever you see a lookups going on, ask yourself whether you should just be including those columns in your index to be able to avoid that extra work. Anyway, let's move on. Incidentally, for non-clustered indexes, we have seen an increase to 1700 bytes in the keys for non-clustered indexes, okay? Your clustered index is still restricted to 900 bytes, but you've got 1700 to play with the keys in your non-clustered indexes, which really helps. But still, plan the size of your columns properly. Don't be making columns that you need to index be, 2000 characters long, or varchar max even, for example. Just don't do that. Make them restricted to how big you actually know that data needs to be, okay? Split your data up. If you've got an address, make sure that you're breaking it up into the city you live in and maybe the postcode and all of those kinds of things that you can search by, rather than just, that free text block of data. I mean, at the end of the day, how useful is it to have an index on, address line 1, which probably starts with the street number? You really kind of need to have that index the other way so that you're searching by country and state and city and those kinds of concepts, more so than starting with the more granular data. Anyway, I figure that typically you index people by last name and then first name, but it's way easier to say Milan than his surname, so I'm going to stick with first name for now. Anyway.
By the time I get famous, everyone will know how to pronounce Sharenet.
This is true. This is true. Everybody will know. I'm not going to try it today. Anyway, let's move on. In 2008, time ticked on some more.
Schumacher. Everyone knows.
Yes, you should change your name to something that people can say. But there's a lot of famous Schumacher, so let's not confuse you with them. In 2008, actually, also in 2005, we got table partitioning, which was interesting because it affected indexing, because effectively every index then started with which partition am I in, and we started to find that. I'll come back to 2008. So we started to find that our index was actually made up of lots of smaller indexes. It was like every partition had its own index. Now, this was fine, except for the fact that if you had a partition per day, for example, because you've got a big table, and then you've got data across some number of years, and you've got like 1,000 partitions, then you would look for a piece of data that you felt that you had indexed, and it would actually have to do 1,000 seeks because it would be doing it per partition. And so a lot of people found that when they introduced table partitioning in 2005, that their indexes, even with included columns, suddenly felt a lot less effective. But actually, the important thing to recognize was just that, well, if you understood that your index effectively started with which partition am I looking at, then you could plan your queries to be able to say, well, hang on a second, let's try and make sure that we can eliminate the partitions that we want, so that we can only have to seek into certain parts of the table. It required a bit of thought, but certainly it became different to how we were doing things in SQL 2000 if we adopted that new feature. I'm going to move on because I'm more interested in things that are less about how you've structured your table and more about how you're using indexes in general. I figure if you've restructured your table to take advantage of partitioning, you should have understood what the impact was on indexing. If you want to talk about that some more offline, then feel free to ping me through the various ways that you know how to ping me. Anyway, 2008. Yeah, I'll try and actually write properly. 2008. There was a couple of things in 2008. One of them was compression. The fact that when a page filled up, you didn't necessarily get a page split straight away. It would then say, well, hang on, let's try and compress this data. And so then all the data would be going in, it would fill up and it would go, hang on, let's try and squeeze it in so that we can put more rows in. And that suddenly meant that using indexes was nice and quick and so on. It was quicker than it was before, because whereas you might have had data that was across 100 pages, now maybe it was only across, well, a whole lot less. Now, the amount that compression works depends on the kinds of data that you've got in there. If you had a lot of included columns that were all kinds of information, lots of different types of things, then maybe you couldn't get as much compression as if, for example, you had, something that was repeated lots of times. More on that later on when we start talking about different kinds of indexes again. But compression certainly became an option that you could turn on an index, either row compression or page compression. Page compression is way better because it would try and compress across the whole page rather than just within the row. But that page compression suddenly meant that our indexes took up far less space. They were still just as heavy to maintain, because at the end of the day, when you tried to put that last row into, a row into that table that didn't fit, it would need to still split it and be able to move some of the data across to another page. But nevertheless, the concept of having to go to disk and pull that information out, it was suddenly a lot less information, and our queries started to run faster if you enabled that option in your indexes. So that was a big deal. But the one that I think was really amazing in 2008 was filtered indexes. Filtered indexes were huge, probably not as huge as included columns, but filtered indexes have the potential to change the way that your application runs significantly. And I find that still a lot of people don't take advantage of it in the way that they should. Because the filtered index is basically like saying, well, actually there's a whole bunch of information in this table that I'm just not interested in. And so I'm not going to include it I'm not going to have those rows in my index. Now understand, your index is a copy of certain columns from a table, right? You might have 10 columns in your table, and you say, I want to index column 3 and column 4, like a composite index on first name and last name. And I want to include columns 7 and 9, because those are the columns that I typically need, right? And that's great. That index serves you really nicely if it's only those columns that you're after. If you're needing to sort or filter on first name, and maybe on last name as well. But if you're not sorting or filtering on first name, then searching on last name alone will be still quicker, because you've got a smaller, you've got a subset of the data to be able to move through, but you can't seek into it if it's not in that order, if you're not trying to leverage that order in your seek or in your order by. But it's a smaller copy of the table, because we're leaving out the columns that we're not interested in. We can still access them through lookups, but we're dealing with a subset of the data according to the columns that we've picked. Oh, filtered indexes lets us filter based on the rows that we want to include. Because I don't know about you, most of the tables that I come across, they have a whole bunch of data that I'm just not interested in. It might be that I'm looking at customers for a client, or products, or I'm looking at applications for insurance, or whatever the case may be, and I'm interested in the ones that are current, but I'm not interested in the archive of 20, 30 years of stuff, right? Because at the end of the day, look, they're there, but I'm not interested in having them in my index. If I need to access one of them, well, maybe in that scenario, I'm happy to be able to go back to a bigger table that's on slower storage or something like that, because you can create an index and tell it to be stored in a different file group within your database, a faster one, for example, for your active data. But if I've got a table that's got 10 million rows in it, but only 200,000 of those rows are the ones that I care about, then maybe I just want to have an index that includes those 200,000. I liken it to the concept of the phone book. Now, the phone book, if I consider the phone book for my whole city is a decent amount of physical book that they give me, right? And when I used to live in London, and the phone book was like, sorry, this way up, right? If I made a pile of the phone books, it would be like this high. It was huge. When I tried to find a cupboard to put them in, it took a lot of physical space, right? But if I wanted just the ones in my local area, just in the region of London that I lived in, those people or those businesses, it was a lot smaller. It was just as quick for being able to find stuff, but it was smaller. It took up less space in the cupboard. Furthermore, if I did need to scan it for some reason, it was going to be a lot less work to scan something this big compared to something this big, right? I mean, I also liken it to people's little black books, people that they used to go out with, the is ex-girlfriend, boyfriend, partner, whatever the appropriate is former significant other, right? Where people have a small little book. They don't have the whole phone book. It's filtered. It's filtered to just the ones that they care about, right? People's personal phone books are way smaller than the book of everyone. Of course, come on, let's face it. We're in IT. We're probably talking about a post-it note rather than a book at all. But still, it's filtered. It's much smaller. We could get away with scanning it if we really needed to, because that's all we care about on a Saturday night when we're feeling lonely and so on. I've been married for over 20 years. This is the whole 20 years of past thing. I've been married for longer than past has been around. I haven't needed a little black book of former significant others. It would be a post-it anyway. But nevertheless, you understand, you don't want to have the whole phone book looking through for those people that you used to date. You just want to be able to have the small list of them, right? When it comes to sending cards during the holiday time, you don't want to have to go through the whole book looking for people that mean something to you. You want a filtered index for that. And it's exactly the same with all those queries at work. When you have things like is active equals yes, right? Or, is from the last year equals something. Last year is an interesting thing because your filtered index can't be changed, can't be on a changeable, that you can't filter it according to 3 months earlier than get date. But you can say, you can create a new filtered index, which is everything since January last year, and then recreate that at some point with a different period, and make sure that you've got predicates in place to be able to help you filter to that, rather than having to look through all of that stuff. But most significantly, you don't have to maintain these, large amounts of data that you're just never going to look at. They're certainly worth considering. They're worth trying to leverage. I wrote a blog post recently at secretperformance.com about whether you should include columns in your index that you refer to in the filter. The basic answer is yes, but mostly you need to understand how the filters work and the times that the query optimizer will be able to leverage those filters to satisfy the queries that you're trying to write. Anyway, filtered indexes, definitely try and take advantage of them. Do make sure that you connect with anti-nulls on, quoted identifiers on, all those things that you should be making sure are set that probably 20 years ago you didn't care about so much, but honestly, use them, because if you don't, you can't actually leverage filtered indexes. You'll get an error if your code tries to change anything with a filtered index. So make sure that you have anti-nulls turned on in all your applications that connect to your database. Otherwise, you'll just regret it. Anyway, so 2008 was pretty significant, but in many ways, not really leveraged enough. Let's move on. 2012. I feel like we're actually getting to the point of finding that we're running out of changes to filters, to indexes. There is going to be one which I refer to as question mark. I'm gonna write 20xx question mark for some features that I would like to see come through that are not there yet, that I hope one day. But there's a big block of stuff that I'm going to talk about for 2012, 2014, 2016. 2017 really didn't have much in the way of changes, and 2019, also not huge in the significant things related to indexes. We've got interesting things like resumable online index rebuilds and things like that, which are great, but I don't feel like they're game changers for how we think about indexes. The things that we have in 2012, 2014, 2016 is Columnstore. And those of you who were paying attention over those years of 2012, 2014, and 2016, well, no, in 2012, we got read-only non-clustered Columnstore indexing. In 2014, we got clustered Columnstore indexing. And in 2016, we got updatable non-clustered Columnstore indexing, which were kind of, just those things of starting with something, increasing it, and then kind of rounding it off, such that across those three releases, we got something that was actually very effective. Let me describe the concept of Columnstore. Basically, way back in my drawing, I had this was what an index looked like. We had the key columns, and we had the being stored in our table here, the order being maintained through slots. When we ran out of space, we needed something that was a level up to be able to say which page the various rows were on. And that's all well and good, but it's row focused. Okay, we would have a row for Milan in Serbia, and Milan would be there along with his country and so on, and that was great. But Columnstore does it differently. And a lot of this comes down to the concept of compression. So what Columnstore does is that instead of storing Milan, Serbia, and the address of the row, which of course is he might have been person 3 in the system. It might have been that actually it's stored on something which is not known to be unique. A clustered, like if you declare your clustered index as unique, then great. If you don't, then you need to have a uniqueifier, because every row needs to have its own address. And you would maintain all of this, including the clustered index key, potential uniqueifier in there as well. I'm just trying to do a U in brackets, but it's not kind of working. And we would have all of these rows like that in a page, and lots of those. Instead, what happens with Columnstore is that we list our data like this. So, for example, if we've also got Rob in there, and maybe we've got Rob in Australia, and I'm number 10, and we've got maybe we've got Eric from past, who was helping to sort that out. He's in Canada, and he might have been number 20. And my slots would tell me that this was first, and then this was next, and this was last in the slot order down here, saying this one, and then this one, and then this one, and so on. Columnstore does it like this. It has a page which stores Milan, Rob, Eric, and it has all of those. And separate to that, it has a page which lists Serbia, Australia, Canada. And if we're talking about, when their first past summit was, we'll have a list of years and so on. And it stores them all separately, column focused, right? The big thing with this is that this can be compressed really easily, right? Because say, for example, that we've got numbers here, and we've got a whole bunch of people that their first past summit was in 2011. A whole bunch of people whose past summits were, well, one was in 2010. A whole bunch of people, their first one was the one in Charlotte. A whole bunch of people. We see the same information being in there over and over and over. And so this can compress really well, right? How many countries are we going to have? Well, probably only up to, 150, 200. There's only that many countries in the world, 200 and something. And so it probably depends on whether you count, each of the countries in in the UK are separate, or whether you're counting sovereignties and all that kind of stuff. It's contentious, the list of countries. But either way, you're going to see a lot of repeated data. And so Columnstore can leverage that with compression. The concept of compression here is, well, I'm a twin. I am a twin. We're not identical. So you still, to describe me and my brother, you still need to actually describe two people. But if we were identical twins, then really it just comes down to being able to say, okay, you can describe Andrew, and then you can describe Rob by saying, well, he's very similar, but he's got a bit more hair, and he's got a spot somewhere, or whatever the case may be. You don't really need to describe two whole different people. You can describe one and then just describe the differences to the other one, right? With data, it's the same. When you start seeing the same information being used over and over and over, this is where Columnstore really comes into its own, because you can have a million rows and you can compress them into the kind of space that would be, well, potentially only hundreds, right? Amazing stuff. In the same way, I mean, you've got page compression. Remember that turned up in 2008, but that, when it's row store, the type of data that you've got is all the information in that row, and you've got lots of different kinds of data. You're not seeing the repetition in the same kind of way, because our countries are still, they're sitting in there next to the first names and next to the year of their first pass summit and all of that kind of stuff, and it's just not as effective for compression. Columnstore flips it around, allows it to be compressed really nicely, and so when you need to scan that data and aggregate across it, as you do in many analytical queries, blindingly fast, like noticeably so, less RAM, all of that kind of stuff. They're very, very effective. Yeah, so 2012, we got to be able to create a read-only, non-clustered copy. We do our ETL, we create a bunch of Columnstore indexes that were read-only. We'd have to drop them, do our next ETL, recreate them. It wasn't ideal, but it was still good for times that you'd load a data warehouse, at night, and then you could recreate your indexes after that. It worked pretty well. 2014, we got clustered indexes, and we introduced the concept of saying, well, let's load up a clustered index called the delta, that when it filled up with about 1 million rows, it would then say, okay, now let's take that away and compress it, and have the data start going to a new block of 1 million rows. And that worked quite nicely. But 2016, we got updatable non-clustered column store. And that's really where the power came in. I did a presentation at the past summit a few years ago on combining that with in-memory, which really is amazingly powerful when you've got lots of data coming in. You want to be able to run analytic style queries against it. You want to be able to have that data be fast, but also massively compressed. And non-clustered column store indexes stored in memory is ridiculously good for that. Close to real-time operational analytics. Amazing stuff. The stuff that is here, which I want to finish on, the thing that I really want to see happen that is not there yet, is to be able to index based on an expression, okay? I want to be able to index something on something like, I want to be able to create an index on date diff in days between the order date and the ship date, for example. Once that data is in, it's never going to change. It's a persistable computed column, but the moment I need to create a persisted computed column to be able to index it, and I would love to be able to create an index on an expression like this. I haven't been able to do it yet in SQL Server. I'm looking forward to the day when I can. I kind of figure that I can work around it with a computed column, but it's not there native. I would like it to be, and I actually think that when this turns up and you start to be able to see the expressions that are used in queries, if you could create an index on that expression, all of a sudden we'd be able to do all kinds of stuff. The worry about adding a computed column is that you don't know if anything's going to do a select star on the table and all of a sudden see something, it's going to break because the application is going to pull an extra row. That worries me. You can't just go adding columns to tables, because at the end of the day, you don't know what your developers are doing. It might even break queries depending on if you've made sure that you've aliased everything correctly and so on. Too many things can break if you add a new column. But if you could just index expressions, then I think that would be huge. This is the next big thing, I think, for indexing. But in the meantime, think about the changes that we've seen in the last 20 years. Path has been around for 20 years. It's fantastic. I thoroughly encourage you to get involved in the Path community. It's changed a lot. It's grown a heck of a lot in the past 20 years, which I think is testimony to the fact that that it's effective and it's part of what the community wants and needs. But being able to see that we've seen changes, we've seen included columns to be able to have to avoid those lookups, to be able to get covering indexes for our queries. We've been able to have filtered indexes so that we don't have to maintain all of that history. We can actually have copies of only the data that we want to be querying in our indexes. Columnstore, of course, is huge for being able to make effective indexing for those large analytic queries that need to be able to trawl through massive amounts of data, because it gets that massive amount of data into a fraction of the space. Indexes have changed. The concepts are still the same. They're copies of the data in a particular order, in a particular style that suits you, and that's never going to change. But if you're still doing indexes the way that you did when Path first started, you need to get more with the times. Thank you for joining us today. Milan, have we got questions?
Yes, well, Rob, we have a couple, but I think you have answered. I will repeat the question. It says,
Sure.
In future, MS will support, I'm sorry, it is from Anaswamy Srinivas, if I pronounce it correctly. In future, MS will support function indexes, like right of last name?
I don't know yet, but I anticipate that they will. I just have no idea when. I don't know if it's in a 5-year plan, a 10-year plan, a 2-year plan. I have no idea. I would like to think that somehow they can, that the people from Microsoft can make it happen in a if not the next release, in the one after it. But it's a big ask. I think it's a big request. I shouldn't use ask as a noun, should I? I would like to think that they will, but we'll see.
Another question. Oh, questions keep coming in. Okay. Let's sort them. Do you have an index, function index now for sorting these questions, Rob?
Nice. I think it's just sorted by time, right?
Yes. Let's say in Columnstore indexes, it's a question again from Anaswamy Srinivas. In Columnstore indexes, how internal search works. I think it's exactly the same as a normal index, as a row store index. He says, example, if I have years from 2000 to 2019, if I search for 2019, does it go on reading 2000, 2001, 2002, and to reach 2019? Does it have to read all 18 years? I think the concept is the same. It has to find the beginning row,
Right. Well, this is an interesting thing, because the way that the data is stored in the Columnstore index is that the rows are in the same order across each of the indexes, because that's how it knows which rows are connected to each other, right? But the key thing is how compressed they are, and so you can get through that data very quickly, right? So it's not so much on can you quickly find the data that you're after. It's about being able to say, can you get through the data very quickly. So Columnstore it's a different kind of concept. So it's not like having an index a separate index per column that still ties to the clustered index key so that you can move through it. It's a different kind of storage, and seeks and scans work a little differently to the way that row store indexes work. we could talk for ages on Columnstore
maybe
indexes.
Just
and I would.
this interesting question. Okay, how does Columnstore index handle a lab column? Thanks. It was a question from Wenzu.
Not nicely. Not nicely, interestingly. So in fact, Columnstore indexes are less effective on data that can change a lot. So my recommendation is to actually think about which columns are across, because the more if they're all just full of random information, like a column store index on a GUID field, for example, on a unique identifier, is it doesn't compress well at all. There's no commonality between the values, and it stops being effective. I would be reluctant to include a unique identifier column in a column store index, except for the purpose of being if that's the clustered index. Of course, it still needs a way of being able to hook back. But that's for being able to search something. A column store index doesn't help on something which is mostly unique. The idea is to use column store indexes for things that you aggregate across, rather than that you search for particular types of data in.
Okay. Well, Rob, I think that's about it.
Fantastic. Well, that's good timing, because I think the next session is coming up in a couple of minutes. Let's go back to the slides so that we can. We've looked at the questions bit, but I'll let you take over. Thanks for moderating, Milan.
Thank you. I think this was an excellent presentation and not so excellent moderation.
Don't be silly.
Yeah. Okay, so thanks everyone. Stay tuned for next session, Dashboard Designing from Zero to Hero with Hasham Niaz. Thanks everyone for putting up with me, and I hope to hear everyone soon. Good luck, and this was a 24 hours of class lecture. I hand it over to organizers. Goodbye, everyone.
Thanks, everyone.